3 classwork problems I want to get through today. On number 7, 2 cars are riding on roads that meet at a 60-degree angle. So I have a car on a road and another road with a 60-degree angle. Car A is 3 miles from the intersection, traveling at 40 miles per hour, while car B is 2 miles from the intersection, traveling at 50 miles per hour. So I'm going to let car A be this side and car B be this side. And when they tell me that car A is traveling at 40 miles per hour, that's the rate of change for car A. So I can call that dA dt. So dA dt is 40 miles per hour. And car B is traveling at 50 miles per hour, so I can say dB dt is 50 miles per hour. And they do tell me that car A is 3 miles from the intersection, but remember that it's changing. So this is 3 miles, so I'm going to record that, but it's changing. So I can't treat that like a constant. And car B is 2 miles, but it's changing, so it's not a constant, so that means I can't plug it in until after the derivative. However, the 60 degree, these are roads, so this is not changing, the 60 degrees. So my 60 degrees is a constant. I'm going to write in constant. So the question is, how fast is the distance between the 2 cars changing? So the distance between the 2 cars is this side here. Since I've called them A and B, I'm going to call this side C, the distance between the 2 cars. So first I'm dealing with the situation where they're both traveling away from the intersection. So car B is traveling this direction. I'll put a little arrow. He's traveling this direction. Car A is traveling this direction. And I'm trying to find the rate of change of the distance between them. So that means I'm trying to find dC dt is what I need to know. So I need an equation of how these are related, how these variables are related. Now, unfortunately, it's not a right triangle, so I can't use SOHCAHTOA. But if you recall, we when the triangle's not a right triangle, we had law of sines, which does not apply here, and we had law of cosines. So just as a reminder of law of cosines, what we would have for that is c squared equals a squared plus b squared minus 2ab cosine c, where the angle C is opposite the side C, so it would be my 60 degrees. So this is just the formula. And when you learned this in trig, you probably learned it 3 different ways, because you also could say a squared equals b squared plus c squared minus 2bc times cosine A. So there's different ways you could write that. I wrote it in the way that makes the most sense for us right here. However, this angle is a constant. It's 60 degrees. So cosine of 60 degrees, and you just need to know this, 60 degrees, you can make a 30, 60, 90 triangle if you want to and do SOHCAHTOA, but cosine of 60 degrees is equal to 1/2. So because it's a constant, I can plug that in. So I'm going to get, I'm going to use capital letters since that's what I chose to use over here. So I have c squared equals a squared plus b squared minus 2ab times 1/2, since that's cosine of 60. So these cancel. So I'm just left with c squared equals a squared plus b squared minus ab. So this is my equation that I need to find the derivative of. So here I'm going to have 2c dC dt equals 2a dA dt plus 2b dB dt minus, I got a product here, a times b, so I have to use the product rule. So it's u prime v, so it's going to be dA dt times b plus uv prime, so it's going to be a times dB dt. That's a lot of stuff going on there. So this kind of relies on us remembering the law of cosines. I don't know if I'm guessing on an AP exam that they would say recall that the law of cosines, they're pretty good about giving formulas like that, so perhaps they would. Anyway, but here we have it. So now I'm actually going to plug in some values. So we know that A is 3 at the point in time we're dealing with. We can plug in A is 3 and B is 2, but I need a value for C. So I have to figure out what C is. Well, remember that we know that from what we just talked about right here, we know that C squared equals A squared plus B squared minus AB. I don't have to worry about the 2a, this whole 2ab cosine C, because we already know that cosine of 60 is a half, and it cancels with the 2, so I can just go right to this one here. So now I'm going to plug in what I know. So C squared equals 3 squared plus 2 squared minus 3 times 2. So C squared is, I think it was 7. So C squared is 7, so C is the square root of 7. So we need that. That's the distance between car A and car B at that particular point in time. So plugging things in, 2 times C, so the square root of 7, times dc dt, which we don't know, this is what we want to find out, equals 2 times A was 3, times dA dt was 40, plus 2, B was 2, dB dt is 50, minus, then in parentheses we had dA dt, which was 40, times B, which was 2, plus A, which was 3, times dB dt, which was 50. Okay, so if you work all this out on the right-hand side, so I'll have 2 root 7 dc dt. You can do the math, or trust me, you get 210. So then we have dc dt equals, if I divide by 2, I get 105. So I'm going to have 105 over the square root of 7, which, if you plug this into your calculator, you will get about 39.686 miles per hour. Okay, so as these cars are traveling on these roads, with this situation that we're having described, at the point where car B is 2 miles away from the intersection, car A is 3 miles away, obviously not drawn to scale, then the rate of change of their distance between them would be 39.686 miles per hour. So that's what we just solved. So that all was part I. So let me see where that would start. Right here, when I plugged it in, is part I. So now let's do part 2I. And in this one, the question says, so now also find dc dt. If car A is traveling away from the intersection and car B is traveling towards it. So car A is still traveling the same way, but now car B is traveling this way instead. So we have to think about how that reflects in our information. And what that means is, what that's going to change is my rate of change for car B. So dB dt is now going to be negative 50. So that's going to be the change here. dB dt is negative 50, but everything else is going to be the same. So we can just plug in. So we get 2 root 7 dc dt equals, and we're still going to have all the same numbers here. The only difference is anytime you see a 50, put a negative 50. So I'm not going to go back to each of the formulas there. So this would be a negative 50 minus, and this is going to be 80 plus a negative 50, or 80 minus 150. So if you work this out, I know this one's pretty involved. When you do the math over on this side, actually I don't have it written down what it was. Oh, look, I have a new memory. I don't have it written down what it was. I only have the answer. So let me just write down, I'll get rid of that. After you divide it, I have 50, oh, I could have worked backwards. 55 over the square root of 7. I mean, I know you can do the math and solve that. So you get approximately 20.788 miles per hour. Okay, so I know that that one was a little more complicated, a lot more complicated. And remembering what the law of cosines was, and then this whole derivative thing going on here, and you have to be careful not to forget any of the parts. So yeah, there we go on that one. Next problem. Beach sand is poured, creating a cone whose radius is always equal to twice its height. So I'm going to draw a cone, and it's oriented this direction. So here's the radius, and here's the height. Forms a right angle with the base, or with the radius. So the sand is poured at the rate, oh, let me put this. The radius is always equal to twice its height. R for radius is always equal to twice its height. All right, the sand is poured at the rate of 20 inches cubed per second. Now, when you want to think about what that represents, you got to look at the units. It's inches cubed. Remember, this is a rate of change with respect to time. I've got a dt on the bottom. This is inches cubed, which means it has to be volume. So that means I need to call this dV dt. So dV dt is equal to, and it's being poured onto this pile, so it's increasing, 20 inches cubed per second. So clearly, I need to deal with the volume for this problem because I'm given dV dt, so I must need the formula for the volume. So the formula for the volume of a cone, and if you didn't know this, you could Google it on the AP exam. I think they would give that to you. So we have 1/3 pi r squared h. And now here I have two variables. So we were given this relation between r and h, so we have to make use of that to replace one of the variables. But then you have to think, which variable do I want to replace? Because it matters. So if you look at what we're solving, it says how fast is the height changing? So we're being asked to find dH dt, which means I have to have an h so that when I take the derivative, I get a dH dt. So I can't get rid of h, I have to get rid of r. So I'm going to replace the r, or the r squared, with 2h. Okay, so then when I simplify this, 2 squared is 4, so I'm going to have 4 pi over 3, and then we'll have an h cubed. So that's my formula for the volume, and now I only have one variable with h, and now I'm ready to do the derivative with respect to time implicitly. So we get dV dt equals, the 3's cancel, and I have 4 pi h squared times dH dt. And now I can actually plug things in. I know dV dt is 20, and we have 4 pi. Part I, which is what I'm solving, says at the time the height is 2 inches. So the height is 2 inches, so I have 2 squared dH dt. So when we solve for dH dt, we're going to have 20 divided by 4 times 4, so we get 16 pi. And this is approximately, well, this can reduce to 5 over 4 pi. And if you use your calculator, it's approximately 0.398 inches per second. Okay, and don't forget the units, and we're talking about the height. Well, the height is a linear measurement, so it's going to be inches per second. Then for Roman numeral, or part 2, now it's when the height is 6 inches. So we still have, we're going to plug into our formula, same formula. So we have 20 equals 4 pi, h is 6, so I get 6 squared dh dt. So when we solve for dh dt, we will get, when you simplify it, because you're going to have 36 times 4, you're going to be dividing 20 divided by that, you get 5 over 36 pi, which is approximately 0.044 inches per second. And I don't just know that. You did it on my calculator. I figure you guys can do that on your calculator. But I do want to point out something. Notice that when the height is 2 inches, so early on, because the height, you're pouring sand. So when you first start pouring the sand, notice how the change in the height is increasing at a faster rate than when the height is bigger. When the height is bigger, it slows, the change in height is slowing down. So it's because it's still positive, so it's still increasing in height, but notice that the rate has is smaller on that, and that should make sense, as it gets taller. So there is that problem. That one wasn't nearly as bad as a law of cosines problem. All right, so now in problem 9, water drains from a conical tank. So now it's going to be oriented this way. Okay, it looks kind of, you know what? After the AP exam, we're going to have a problem of a melting ice cream cone. And then we're going to go get ice cream. Okay, water drains from a conical tank at the rate of 2 meters cubed per second. So again, it's meters cubed. So that should tell you this is volume. And because it's draining, that tells me that it's decreasing. The water's decreasing. So I'm going to put a little water level in here. So we have dV dt is negative 2 meters cubed per second. So we've got a radius. Now, we have the radius of the tank, but we also have the radius of the water level. So I'm going to call this radius a little r, and I'm going to call this radius a capital R, just to kind of show the difference between those. And so this right here would be the height of my cone. I'm going to call that a capital H, but then this would be the height of the water level inside this conical tank. And that's actually kind of important here, what I've just kind of created with these. I drew the height here instead, but I could have drawn it here. And we end up with similar right triangles, and I'm going to have to make use of that to relate my variables. Anyway, the tank is 16 meters high, so that is the capital H. So I'll go ahead and mark that. So that's 16 meters. And the top radius is 4 meters. All right. How fast does the water level fall? Well, the water level falling means I'm looking at the rate of change of the height. So I'm looking for dH dt. That's what I want to find out. So I need to know that. And then it says when the water level is 12 meters high, and then when the water level is 2 meters high. So I need the volume of a cone, which we just did in the last problem. We got 1/3 pi r squared h. So again, we have two variables, and I only want one of them. As a matter of fact, I want the h because I'm solving for dH dt, so I need to keep the h. I need to get rid of r squared. So I need a way to relate R and H. So this is what I've got to work with. And what I'm going to use, on the last problem, it was kind of simple because they told us flat out that R is always equal to twice the height. Well, they don't give us any information like that. But we do know that we've got similar right triangles. And so I can say that this capital R, which is 4, actually I'll start with this little r. R is to 4 as H is to 16. Okay, so I'm just using similar right triangles, and I'm creating a proportion. So this radius of the water, R, is to 4, which is the radius of the tank, as H, the height of the water, is to the height of the tank. So that's my proportion. So then we have 16R equals 4H, and R equals 4 over 16, so we have 1/4 H. So now I can take this and plug it in for R. So I get V equals 1/3 pi. In place of the R, I'm going to put 1/4 H squared times H. All right, so I'm going to square the 4 down here. I'm going to get a 16. 16 times 3 is 48. So I'm going to have pi over 48, and this is going to be H cubed. So that's my equation. Now I need to find the derivative with respect to time implicitly. So I get dv dt equals, going to bring the power down here, and it cancels, leaves a 16 on the bottom. So I'm going to have pi over 16 H squared times dh dt. And now the hard part's over. I can just plug in my values. So we know dv dt is -2. I'm solving part I. And we get pi over 16. H is 12. So when you solve this, so we're going to take the -2, divide by 144, multiply by the 16, divide by pi, all of those things. You will get -2 over 9 pi, and you can check that. So that is approximately -0.071 meters per second. And then for the second part, plugging in again, the only difference is H is 2. So we have -2 equals pi over 16, 2 squared dh dt. All I'm doing is plugging into this formula the parts that we know. And when you solve for dh dt, you will get -8 over pi, if you simplify that, which is approximately -2.546 meters per second. And again, getting the units, we were finding dh dt, which is a linear measurement, so it's not area, we're not squaring, we're not cubing, so it's just meters per second. All right, so you have an assignment to work on. So hopefully, if you need to look back over these again or slow it down, I know they're difficult, but once you get them, they're not too bad. So